Hey, welcome everybody. My name is Danny Elegante, and I'm up in Madison, which is up by Huntsville. We are nice and dry compared to a lot of the state that's very, very wet. So hopefully everybody made it through all the weather okay. And we're always praying for all the people that were in harm's way. So hopefully they're okay. But today we just kind of want to get going on a little bit on Unit 2 in AP, and this is all about Lewis structures. So last week was all about bonding. So metallic bonding, ionic bonding, what are those things? And this is just an extension of that. Today we're going to look at pretty much just the covalent bonding. So the Lewis structures, the electron dot structures, you may have had them called. To answer your questions, if you have a question, feel free to unmute your mic and speak right up. And you can also type in the chat box. And if you don't know where that is in Google Meet, if you kind of wiggle your mouse down there, you can find a box that says chat with everyone. Mine looks like a little voice box, a little call out with a 1 circle around it. So feel free to ask all the questions. The other thing you'll notice on your screen is I've shared with you a pair deck. And a pair deck is just like a PowerPoint or a Google Slides, except it asks you to do things. So instead of just me talking and you listening, I'm going to ask you several times along the way several times to answer a question or to draw or something like that. So if you will go to joinpd.com and type in that code IOYIJB, and just in case you forget that code, it'll still be on the screen that I'm sharing with you here in a minute. But remember that Pear Deck just allows you to do things. So you'll answer questions and draw and all that kind of thing. And just a reminder that this is being recorded and it'll be viewable later. So any questions, y'all please jump in and ask away. So with that said, let's go ahead and start class. I'm going to swap over and share what it looks like as a student so that I can kind of keep y'all. Oh, sorry, that's not right. Hang on. There it is. All right. So right now, is everyone seeing the thing that says Week 4 Webinar Unit 2 and Slide 1 of 37? Hopefully so. So if that's true, then you're in the right place. So let's go ahead and we'll go ahead and start. Sorry about that. So covalent compounds, electrons are shared. So we know in a covalent compound, usually 2 nonmetals, the electrons are shared between the atoms. You can share 2 electrons, you can share 4, or you can share 6. So 1 pair, 2 pair, or 3 pairs. But we also have to remember that when we form that covalent bond, we really have to look at what's going on between those atoms. So before, you've probably learned the idea of periodic trends, electronegativity, atomic radius, and some of those. Those things have to do also not just with individual atoms, but how individual atoms then get together and form bonds. So as the electrons get closer to each other, there's a repulsive force. So the electrons from one atom, the electrons from another, as you start to bunch them together, there's a repulsive force. But there's also an attractive force. So the electrons are attracted to the nucleus of the other. You guys have all experienced this. When you get close to somebody, when you walk up to somebody, you don't stand right up next to their face. That's because there's a repulsion going on there. And you know, if you had somebody who's a close talker, somebody who gets right up in your face and starts talking to you, your natural inclination is to take a step back. So you want that magical point where the forces of attraction are equal to the forces of repulsion. And we call that the bond energy, and we call that the bond length. So this is that same idea, except in graphical form. As the molecules are really far apart, they're checking each other out, but there's not a super strong force of attraction. As they start to get closer and closer, notice that that graph really dips down. And as you're dipping down right there, the molecules get, the atoms get closer and closer together. And at some point, they get too close together and they start to have a force of repulsion. So you want to land right here in this sweet spot right here. And that sweet spot will be the point of lowest potential energy. So notice if the atoms start up here and end up down here, that's a drop in potential energy. So when a bond is formed, energy is released. And in order to undo that, to break apart that bond, energy has to be absorbed. So breaking bonds is endothermic. It takes energy to break those suckers apart. When bonds are formed, energy is released. And we talked about that a little bit last time with lattice energy and the idea that when you form an ionic bond, energy is released. And this carries over also into covalent bonds. So we can measure the bond length by going over on this graph and measuring this distance on the x-axis. And we can measure the bond energy by looking at how much the y-axis changes. So here's a graph right here, and you should see a green on your pair deck thing. You should see a green arrow that's pointing down. So if you could drag that green arrow to the point of maximum repulsion when molecules are too close, where molecules are too close. So go ahead and grab the thing and pull it to where you think that is. Okay, looks like y'all are pretty much dead on. For the most part, y'all are saying, hang on. I think I was sharing the wrong window. Hang on just a second. Okay, so most of y'all said way over here at that far right, and you are right. That is way too close, a lot of repulsion. So if you could go ahead, drag the icon, it should still be draggable. Drag the icon to where do you think is the ideal place where the force of repulsion is equal to the force of attraction. So where would be the bond length and the bond energy, that perfect spot where attraction equals repulsion? You still ought to be able to drag that. And I apologize for my dog. My dog is seeing a cat or something outside, and he's very knowledgeable. So you can tell that that's exactly right, right there at the bottom of that spot. So most everybody got that right, and that's great. And so that's that spot that we're looking for, and we would call that with the point where you can measure the bond length and the bond energy. All right, so let's keep going. Now, you drew Lewis structures in chemistry, or you should have. Even with COVID and messing up the school year and stuff like that, most all of y'all have seen Lewis structures before. All right, so what I kind of want to walk you through is this idea of Lewis structure of drawing little dots around everything and then circling certain things is not really the way that we want to head to doing Lewis structures. The idea here is we want to move to doing this last water molecule. We want to show bonds with single lines, and that means 2 electrons being shared. And then we want to have other electrons in pairs. So you would have 2 electrons above the oxygen and 2 below. We really want to get away from circling a bunch of electrons. But the whole idea behind Lewis structures is hydrogen only has 1 electron, but it would like to have 2. Oxygen only has 6 valence electrons, and it would like to have 8. But there is no taking and giving. This is not an ionic bond. It's not that hydrogen wants to get rid of one and oxygen wants to take it. Everybody's looking for electrons. So this is a I want. So in a Lewis structure, we're trying to say which electrons are being shared. Because if you share electrons, then you're saying those electrons are available to all the atoms that are sharing it. So you can have a single bond where 2 electrons are being shared, a double bond where 4 electrons are being shared. And again, we want to show double bonds as 2 lines. And you can have a triple bond. So it's kind of like going to Wendy's. You can get a single, you can get a double, or you can get a triple. Now, you can get a quadruple at Wendy's. It's off the menu, but you can ask for it. But I will tell you that you cannot have a quadruple bond in chemistry. And the reason for that is all those electrons being shared in that same space, it's too much. Electrons don't like each other. There's a repulsion among all those electrons. So in a triple bond, you've got so many electrons in there, that's the most that you can fit in between those 2 atoms. All right, so something for you to drag. So if you would, I want you to drag, you should have a red line that you can drag. You should have an equal sign, and you should have a taco. I couldn't find is equivalent to sign. So if you would, drag the taco to where you think the triple bond is. Drag the equal sign to where you think the double bond is, and drag the red dash to where you think the single bond is. So that red dash is a big red line up top. So you can drag the red line to wherever you think the single bond is. So either A, B, or C. Drag the equal sign to where you think the double bond is, and then drag the taco to where you think the triple bond is. As if you might notice, I'm pretty hungry. I haven't eaten lunch yet. So that's why I grabbed a taco, because a triple taco sounds really delicious right now. So let's see what y'all got. Okay, so pretty darn good. Pretty darn good. Now, I did get a couple spots out of order of where I would think they are. So let's talk about where these things actually are. So see this huge drop in energy by curve A. That huge drop in energy by curve A means that's a stronger bond. That's a greater bond energy. More energy was released when that bond was formed. So we say that a triple bond has a greater bond energy than a double bond, and a double bond has a greater bond energy than a single bond. So just on bond energies, we would say this hugest dip would be the triple bond. So in A, that would be the triple bond. The second biggest dip in B right here, that would be the double bond. And in C, that would be the single bond. So the correct placement of all those things is taco at the bottom, double bond here at B, and then drag that red line down to C, right? Now that's based on bond energy. Let's see if we can also do that based on bond length. So look at the distance from kind of where you started out here to the edge. Notice how C has got a greater distance. Kind of, if you start at the green line, just take that as your starting point and go out. Notice on the x-axis, the bottom of that C curve is the greatest distance, and then the bottom of the B curve is the next greatest distance, and then the bottom of the A curve is the shortest distance. So this also helps us because a single bond has the longest bond length, and then a double bond has a shorter bond length, and then a triple bond has the shortest bond length. All right, and this is just proof that I'm not making stuff up. You can see that between 2 hydrogens, it's 74 picometers, whereas in between between hydrogen and a big atom like iodine, it's 161. And you can see in there, if you look, that the carbon-carbon single bond is 154, the carbon-carbon double bond is 133, and the carbon-carbon triple bond is 120. So we can judge bonds based on their lengths or their energies. All right, so this just goes back to that bonds. So notice that to break those apart, it's going to take this amount of energy to break those apart. And that bond energy differs greatly, again, based on Coulomb's law. If Coulomb's law is attracting everything together, then that is also the same amount of energy or force that must be applied to break them apart. So all these bond energies that are here, you'll see delta H later. It becomes much more important later. But for right now, just realize that the bond energy here is a relative way to look at and go, oh, this bond must be stronger than this bond, kind of a thing. We can also have nonpolar covalent bonds and polar covalent bonds. So this is fairly straightforward. When I was a young man, we had to, oh yeah, where can you find the presentation code? Sorry, John. John, the presentation code is IOYIJB. IOYIJB. Sorry about that, man. So let's see, where was I? Okay, so you can have polar or non-polar bonds. When I was a young man, my brother used to take stuff from me because he's much bigger than I was and he's 4 years older. So while we were supposed to share certain things in our room, what that really meant was he got them most of the time and I didn't get them just because he had a much stronger pull on those electrons. So same thing in between atoms. Now, how do you measure who has a stronger pull on the electrons? Same thing we have been doing all along. Ever since Unit 1, whoever has, or if you're worried about distance, according to Coulomb's law, it's all about who's got those valence electrons closest to the nucleus. So we really measure this pull on electron as electronegativity. So we would say here that fluorine has a much greater electronegativity than hydrogen. It gets the electrons most of the time. And this little funny Greek symbol over here that looks like a fancy D is actually just like a partial negative charge. So that means the fluorine's a little bit negative and the hydrogen's a little bit positive. And we say whenever a molecule has two different charged ends, like a positive and negative, we say it's polar, just like the Earth has a north and south pole. So we're going to be talking about polar bonds, and we're also going to be talking about polar molecules. Right? How do we decide whether things are nonpolar, polar, or ionic? We really do it based on this number scale. So when you have a very small difference in electronegativity, we call that nonpolar. So carbon and hydrogen has an electronegativity difference of 0.4. And we say anything that's a hydrocarbon. Hydrocarbons are things like wax, gasoline, asphalt, anything that's a hydrocarbon, just carbon and hydrogen, is a nonpolar compound. They don't really like to mix with water. So anything in that 0 to 0.4 range, we would call nonpolar. Anything that's greater than 1.9, so let's say 2 and above, we would call ionic. And ionic things happen between things that are metals with a very low electronegativity and nonmetals, things that have a very high electronegativity. So looking at these numbers, you're going to need those in a second. So burn those into your head. Very low is nonpolar. Anything greater than 2 is ionic. And then anything in between, so 0.5 to 1.9, we would call that a polar. And don't get caught up in, is it polar or is it ionic? Ionic is just something that's so super polar that it steals the electron. So imagine a situation where you have an older brother or sister, and instead of sharing something with you, they're just so big and bad that they just whoop, take it away from you. That would be so polar that you don't even get it any of the time, and that would be an ionic bond. So this is your turn to shine. So the question's going to come up. Take one more look at the numbers. All right, let's see you classify those bonds. You can draw, so you get to pick either a pen or a pencil, a stylus, text box, and you get to pick a color. So for each one, cesium and chlorine, you can guess it as either polar, nonpolar, or ionic. Those are your choices. And hydrogen and oxygen, answer that one too. And then for 2 nitrogens, would that be polar, nonpolar, or ionic? So go ahead and classify them as ionic, polar, or nonpolar, each one. Just draw anywhere on the slide, and we'll see what y'all's answers are. Okay, so a couple of y'all are answering, just kind of answer out to the right. So we're talking about not cesium or chlorine. I'm talking about the bond between cesium and chlorine. Is that going to be ionic, polar, or nonpolar? So you shouldn't have 2 answers for CSCl, right? So just off to the right over here in Cl, we just want you to write. Let's see if I can do this. I'm a horrible drawer, so let's see if I can make this work. So for instance, I may choose to plug in my bamboo pad so I can actually write something. Okay, and so I may choose like nonpolar here, and so I would write nonpolar. So that's kind of what I'm looking for you to do. So go ahead and write polar, nonpolar, or ionic, or you can just write NP, P, or I if you want to. All right, so let's see how we did. Oh, nice. Some of y'all typed it out. Very good. Great. Okay. So, so my answer is going to be, this is 3 and 0.7. So 3 minus 0.7, because remember, it's based on electronegativity difference. 3 and 0.7 gives us a difference of 2.3. And we said anything greater than 2 was ionic. So the bond between cesium and chlorine is ionic. And that's because of the electronegativity difference. It's also because it's a metal nonmetal. No great big surprise there. So that one should be okay. So, all right. So let's try the hydrogen oxygen. So between hydrogen and oxygen, 2.1 and 3.5. Don't worry about negatives. Just get the difference between them. The difference is 1.4. And the difference of oxygen and hydrogen 1.4 means that's polar. And it's not just polar, it's really polar, right? So this is one of the reasons later in future units, you'll learn about hydrogen bonds, and you probably have heard that before. But hydrogen bonds occur between things that are really polar. So that hydrogen oxygen would definitely be polar. And what is it between nitrogen and nitrogen? Well, the electronegativity difference is 3.0 minus 3.0 is just 0. So something that is sharing electrons with itself, who is pulling harder? They're both pulling equally. Since they're both pulling equally, it doesn't really matter. The pull cancels out. So we would call that last one, nitrogen, nitrogen, we'd call that nonpolar. So it went ionic, polar, and then nonpolar. Right. So this is just a how to do Lewis structures. Now, your teacher may have taught you different, and that's fine. There is no one way to do this, but there are lots of wrong ways to do this. So the idea is just to clean it up so that you kind of get an idea of what you're doing, not that you're just following steps. So the idea is to count up the total number of valence electrons. So if you have a periodic table with you, or maybe on your computer or print it out or something like that, if you could grab that now, and once you have that periodic table, we're going to teach y'all how to find valence electrons. So one of my favorite periodic table of all time is Webb Elements, even though they have ads. And in order to find valence electrons, you're just going to go to the group number. Nitrogen has group number 15. If you were to write out the electron configuration for nitrogen, you would say 1s2, 2s2, 2p3. So our valence shell is the outermost shell that has electrons, the outermost occupied energy level, and nitrogen has 5 electrons. You get that from the electron configuration, but the quick and easy way to do that is to take the group number and subtract 10. So 15 minus 10 is 5. Nitrogen has 5 valence electrons. Chlorine's in group 17, and it has 17 minus 10 is 7 valence electrons. Don't come over here and tell me hydrogen has got 1 minus 10 is negative 9 valence electrons. Nobody likes a smart aleck. So if it's less than 10, then it's just a group number. So hydrogen has 1 valence electron as we're going. All right, so figure out how many valence electrons you have. If it's a polyatomic ion, like let's say nitrate. Nitrate is NO3 with a -1 charge. So we would take the number of valence electrons in nitrogen is 5. There are 3 oxygens, and each oxygen has 6 valence electrons. It's in group 16. And so that's a total of 23 electrons. And then we add 1 more electron because nitrate has a -1 charge. So all together, you would have 24 electrons. If it has a positive charge, you just take 1 away. That's how many electrons you're allowed to spend. Then somebody has to go in the middle. You're going to start hooking things together. The least electronegative element goes in the middles. How do you know what electronegativity is? Well, it's not on your periodic table. So who's the most electronegative element out there? Fluorine is the most electronegative element on the periodic table. So if you're thinking in terms of periodic trends, just think of greater electronegativity to the right and up, in case you need to make those decisions. Now, who is never allowed to be in the middle? Hydrogen. Why is hydrogen never allowed to be in the middle? Because hydrogen can only form 1 bond. If you were in a situation where hydrogen was in the middle, it couldn't link up with a bunch of things. It could only link up with 1 other atom. So hydrogen never goes in the middle, always goes on the outside. You connect everybody with a single bond. So hook them together with a single bond. If you have electrons left over, which you should, then you put them around the outer atoms. And then if you still have electrons left over, you put them on the central atom. So for example, if you were going to do water, so H2O, that's a total of 8 electrons. And you put oxygen in the middle because hydrogen can't go. And then you'd hook them together with single bonds. Single bonds represent 2 electrons. So that means every time you have a single bond, you spent 2 electrons. And then anything extra first goes on the outer atoms. Hydrogen only needs 2, so hydrogen doesn't get any more. And then if any electrons remain, they go on the central atom. So for water, they would go on that oxygen. So this is the idea. So you hook them together. You make everybody on the outside have 8. We call that satisfying the octet. If there are some left over, they go on that central atom. Double and triple bonds are only if absolutely necessary. So a lot of people try to be like, I'm going to put a double bond on everybody. You get a double, you get a double, you get a triple. And that's not how things work. That should be one of the very last decisions you make when you're writing a Lewis structure. Only if that is the only way to form an octet. Now, general note, hydrogen is okay with 2, so it doesn't have to have 8. That's fine. Beryllium, and if you look up at it, it's like element number 4. So it's right there on the periodic table at the very top. It's happy with just 4 electrons. And boron's happy with 6. So if you get one that has 6, then that's okay. And with boron, but everybody else is going to want to have 8. Carbon, fluorine, everybody wants to have 8. So let's see how we're doing. So let's try one out. So CO2, this is your chance to draw on this slide. So if you could go ahead and draw out what you think the Lewis structure for carbon dioxide would be. Now take your time, look at your periodic table, figure out how many valence electrons carbon has and how many valence electrons oxygen has. Add them all together so you know how many electrons you have to deal with. And then just think through the steps. What's the next step? Okay, after I have my valence electrons, least electronegative in the middle, so carbon in the middle. Hook everybody else together with single bonds. So oxygen's on the outside, carbon in the middle. And then work on distributing the rest of electrons. So y'all go ahead and draw what you think the Lewis structure is. And I know it'll take you a minute. It doesn't have to be any certain shape. It just has to be a Lewis structure. And I'm just looking over what y'all are doing. And keep in mind, if you're not making mistakes, then you're not learning. If you knew everything that you needed to know coming into this, then I just don't know why you would come to this. The goal is to learn. So if you're making mistakes, then that's exactly what we want. Seeing some really good answers. Seeing some not so good answers. At least one of y'all should be a member of Congress. You are spending way more electrons than you should be. Hang on. My dogs. I apologize to those of you listening to this on YouTube because you too get to listen to my dogs. So we have two dogs, Cooper and Maggie. You're just hearing the one. So carbon in the middle, oxygen on the outside. If you did what I did, carbon had 4. Each oxygen had 6, which is a total of 12 electrons. That means I have 16 to spend. So carbon's the least electronegative. I hook everybody together with single bonds. So that means I just spent 4 electrons because there's 2 in each bond, right? Then my next goal was to give everybody on the outside 8 electrons. So the oxygen just sees 2 right now. And for it to see 2, that means it needs 6 more. So I got 1, 2, 3, 4, 5, 6. So that oxygen is good to go. And this oxygen over here also needs 6. 1, 2, 3, 4, 5, 6. And if I added up the 4 electrons in the bonds and the 6 electrons I spent on one oxygen and the 6 electrons I spent on the other oxygen, that gives me a total of 16. So I've spent all of my electrons. I'm not allowed to put electrons anywhere else. I'm done drawing dots. I can't do that. So is this oxygen on the left, does it see 8 electrons? Yes. So that oxygen is satisfied. It's good to go. The oxygen on the right also sees 8 electrons. So 1, 2, 3, 4, 5, 6, and then 2 in the bond that are being shared. So it too is satisfied. It has 8. But this carbon in the middle is very sad because this carbon in the middle only sees 4 electrons. Well, I can't just draw electrons on there because I'm out of electrons. I can't draw anymore. So this comes back to that very last step. The very last step is feel free to move electrons into a double or triple bond if you find that it helps. So I'm going to erase. Now, if you erase and it doesn't help, then you can always put them back. So this is definitely something you want to do in pencil. So I'm going to take one lone pair from the oxygen and I'm going to turn it into a double bond. So this is no longer This is 2 shared pairs of electrons. Now, that oxygen on the right still sees 1, 2, 3, 4, 5, 6. Remember, there's 2 in each bond, 7, 8. So that oxygen still sees 8 electrons. The carbon sees 1, 2 in the first blue bond, 3, 4 in the second blue bond, 5, 6 in the third blue bond. In the orange bond. So it's getting better, but carbon still doesn't see 8. So what is that last step? That last step is still, you can move any pair of electrons. It doesn't matter what pair you move. I'm going to move that pair, and I'm going to turn it into a double bond. Now, that doesn't affect the oxygen. Instead of oxygen having 6 and 1 shared pair, now it has 4 shared electrons and 4 electrons that it keeps to itself. But look at the carbon now. Carbon sees 2 in the orange bond, 2 in the blue bond, 2 more in the blue bond, and 2 in the purple bond. So this is an example of a successful Lewis structure that accounts for all the electrons. And a lot of y'all got this right as you were doing it. That's good. A couple of y'all overspent your electrons, and that's okay too. But just remember, you can't spend more electrons than you actually have. All right. Now, here's my question. Which one is right? So what I want you to do is draw on this slide any of the ones that you think are not right. Just put a red line right on top of that structure that's drawn. Okay, while you're doing that, I now have to let my dogs out because they're going crazy. All right, come on, let's go. And I'm back. It's just like virtual learning. Okay, so let's see what y'all drew. All right, so one of y'all said IDK, and one of y'all said they're all okay. And so the person that's right is the person that said they're all okay. Believe it or not, there's nothing wrong with any of these structures. So look at each one for a second and say, does everybody still see 8? If there's 2 in each bond, and you count the lone pairs, turns out every single one of these structures is totally fine. It doesn't break the rule of Lewis structures. We will look at a technique next week where it's called formal charge, where you can look and go, oh, wait, I can figure out which one is better, right, in AP. But for right now, we're just drawing the Lewis structures. So that was a trick question on my part, but I really appreciate y'all's answers, especially the IDK. All right, so take a stab at this one. Go ahead and draw what you think the Lewis structure is for NCl3. So this time, nitrogen needs to go into the middle. I know it's not the least electronegative, but for this thing to work, nitrogen goes in the middle, and then the chlorines go around it. So I'll go ahead and put nitrogen and the chlorines. So you've got to draw in everything else. So remember, your first step is to find your electron budget. So figure out how many electrons you have. And that's the group number minus 10. And that'll give you a total number of electrons. And then try to draw the electron structure. I'm getting some really good answers. This is great. So remember, the trick here is everybody gets a single bond. So start out with a single bond between each N and the Cl. And remember, every time you make a bond, that represents 2 electrons. And then the next step was take the other electrons that you have in your budget and go ahead and put them around the outside atoms to give everybody 8. And then if there are any left, they would go on that central atom. And then the very last step is you would make a double or triple bond if it helps, if it's needed. If it's not needed, if you've put down electrons and everything looks great, everybody has 8, then there's no need to make a double or triple bond. So a couple of y'all are still working, and that's fine. Let me go ahead and clear something up. Some of y'all added up your electrons wrong. Remember that it's NCl3. So your budget is not 5 plus 7. It's 5 for nitrogen plus 7 plus 7 plus 7. Each chlorine has 7 electrons. So remember, otherwise you're never going to be able to finish because you won't have enough. Nice. Somebody really drew this up with some blue dots. That's beautiful. I like that. Somebody did purple. That's nice. Oh, wait, that's me. Sorry. I did a really good job. All right. Now, the other thing I want you to, I'm looking over y'all's answers. I want y'all to think, how many electrons, what is the most number of electrons that an atom typically can have? We would typically say it's 8. So no element can see more than 8 unless it has d orbitals. So d orbitals actually happen in the 3rd energy level. So in the 3rd energy level, that's where we get those 3d electrons. And we can exceed the octet. So you can actually have more than 8 if need be. But nitrogen is not in the 3rd row. Nitrogen's in the 2nd row. So I saw at least one of you have like 3 double bonds. And 3 double bonds would be 6 bonds. 6 bonds, each with 2 electrons, would be 12. You just put way too many electrons into nitrogen. It doesn't have enough room for that. So you got to remember the middle one has to have 8 as well. So I'm going to go on and we're going to go ahead and look at the answer as y'all are going. So let's see if this one's okay. So your budget here was 5 for nitrogen, 21 for all the chlorines. That's a total of 26. So we made a bond between each nitrogen and chlorine. Then we went around and sprinkled in pairs electrons, and those electrons went all the way around for all the chlorines. There were 2 left over, and so we put 2 on that middle nitrogen. And if you notice, there's no room, there's no need for a double or triple bond because that nitrogen has 8 electrons. It has 3 bonds, each with 2 is 6. Plus 2 more makes a total of 8. So that's 8 electrons, and that's good right the way it is. It doesn't need any change. Let's try another one real quick. This is HCN, and it goes exactly in that order. So you don't have to figure out who goes in the middle and all that kind of thing. It literally is going to be H, and then a C, and then an N. And obviously, this is a practice skill, something you need to practice. So go ahead and draw out what you think the Lewis structure for HCN is. Remember, total number of valence electrons. Everybody gets a single bond. Start handing out the electrons to the outside atoms. If there's anything extra, put it on the middle atom. And then finally, make double or triple bonds if need be. So hydrogen would have 1 valence electron, carbon would have 4, and nitrogen would have 5, as y'all are figuring out your budgets. I don't know if y'all are drawing on your phone or a tablet or what. Y'all are way better than most people I know. If you're drawing with a mouse, God bless you, because that's tough. I'm drawing with a little tablet with a stylus, and I can't draw. So y'all are coming along. I'm seeing a lot of right answers. And there is only one way to make this work. So there is wrong and right in this case. So let's walk you through kind of what my thought process was. And y'all can agree or disagree or ask questions as you go. So everybody gets a single. That's 2 electrons. So that means I spent 4 electrons on bonds. And then I went 1, 2, 3, 4, 5, 6. Because nitrogen needs a total of 8, so 2 in the bond, 6 on the outside. Hydrogen doesn't need any more. It's good with 2, so it's good. But I'm not done here because I've spent all my electrons, 4 on the green bonds, 6 on the dots, and the problem is that's 10. That was my budget. That's how many electrons I had. So I can't just go dropping them in here like do like that, right? Because that's not allowed. You're spending electrons you don't have. So this is that very last step. Is there a way that you can move a lone pair into a double or triple bond and see if it helps? And you can definitely move one lone pair here into a triple bond. Into a double bond, sorry. And then you can move another lone pair here into making a triple bond. And you see that HCN, hydrocyanic acid, or hydrogen cyanide, has that Lewis structure. And a lot of y'all got that answer right. That's great. So try this little bit of a tougher one. Sulfur in the middle, fluorine on the outside. Sulfur is going to have more than 8 electrons. So I'll go ahead and give you that hint. Go ahead and draw what you think the Lewis structure is for sulfur tetrafluoride. It'll have more than 8 electrons around it, the sulfur will, when you get done. I'm still here. I'm just looking at your answers, so keep going. At least one of y'all is throwing a bunch of double bonds in there. And remember, double bonds and triple bonds have to be the very last thing you do. So if you don't have dots around the fluorines, then you have no business doing anything with double and triple bonds. So remember, the idea is to go around the outside with any remaining electrons and make the outside atoms have 8 first. So save that double or triple bond for that very, very last step. So one of you dropped a question mark on there. You're right on. Can you move your lone pair so it doesn't look like it's right there on the bond? You know who you are. Other than that, you're great. There you go. All right, black letters with green dots, you dropped 1 extra electron. That top left fluorine's got 1 extra. I think you probably just dropped a pencil, to be honest with you. These are actually some really good answers. So just to double check as we go, SF4, your budget is 6 for the sulfur, and each fluorine has 7. So 4 times 7 is 28, plus 6 more from the sulfur means that you have a total of 34 electrons. So you should be spending 34 electrons. And so far, so good. We're going to go ahead and go on because I want to make sure we see this one more that we want to do. And this is the actual Lewis structure. So I hooked everybody together with a single bond, like you're supposed to. And then fluorine needs 8. So each fluorine got 6 more dots. That's the idea. Go around with the extra electrons. So each fluorine got a bond, which is 2 electrons. And then it got 6 electrons in lone pairs. So I've spent 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28, 32. And I have 2 electrons left over. And remember, the step is put them on the central atom, because when you put them on the central atom, that's where it can go, is that thing right there in the middle. Sulfur is going to have more than 8 electrons, and that's okay, because sulfur is in the 3rd row or below on the periodic table, and so it has a 3D orbital. So we can have what's called, the fancy word is called the expanded octet. So this is the Lewis structure. Now, a lot of y'all drew it as a big X. That's fine. It doesn't have to be this shape. It just has to throw in the electrons. And then you can start thinking about what is the shape of something like that. Right? So far, so good. We're going to do one more, and we'll let that wrap up for the day. And then we'll kind of pick up here next week. So if you were here this week, we want you to come back next week. It's going to be a slightly different time, and Matt will remind us before we go. But we're going to just take this idea of what we're doing, and we're just going to keep building on it, because when you have Lewis structures, you can do lots of things. You can figure out, hey, what's its geometry, its shape? Is it linear? Is it, what shape is it? We can also figure out, is it a polar molecule or not? So this becomes a building base, right? You have your Lewis structure, and then you could do a bunch of other stuff on that. So here's your last one. Go ahead and draw in xenon tetrafluoride. Now, you may have been taught in physical science or in chemistry before that the noble gases don't form compounds. And that's not exactly the truth. Xenon is a noble gas, and But the noble gases, especially the really big ones like krypton, xenon, radon, can form compounds if you put them really close together and you apply a lot of heat and pressure. You can really get the molecule or the atoms really close together. They do form molecules. So go ahead and draw what you think the Lewis structure for xenon tetrafluoride is there. Xenon in the middle, put it in the middle, and then the fluorines around it. Y'all are getting so much better. So wow, one of y'all killed it. Not in a bad way, a good way. You got it. You were awesome drawing it. While y'all are drawing, I just wanted to touch on the AP exam. Are they going to make you draw one of these on the AP exam? Oftentimes, yes. But oftentimes, to make it easier, they'll put in the XE and the F's around it, and they just ask you to fill it in. Or they will say, here's two Lewis structures. Which one is better? Or they'll say, here's most of the molecule. We left this end of the molecule. You can do it that way. And sometimes they just ask you to continue on. So once you drew it, can you tell me the shape? So stuff we're doing next week, can you tell me whether it's polar or not? So just drawing a Lewis structure is oftentimes worth between 1 and 3 points on an FRQ, a free response question. So this is a very important skill in AP chemistry. All right, some of y'all are getting happy with the double and triple bonds. Again, you should save the double or triple bonds till the very end. Somebody's jumping ahead and they're telling me it's polar. Don't know if I agree with you, but good for you that you expressed that opinion with a question mark. I see you. I see you. So, and one of y'all said NP. All right. So, y'all are getting so much better. I just have to show you. Y'all had some great answers, and you got there really fast. Here's the thing. This is what it should look like. Thing I want you to realize is xenon can have more than 8 electrons. In this particular case, xenon has 4 electrons in each one of the bonds. So, xenon has 4 bonds, each with 2 electrons. So that's a total of 8. And then it has 2 lone pairs. So that would be a total of 12. And that is a lot of electrons. Xenon can handle that, though, because it's in the 3rd row and below. Fluorine cannot see more than 8. And your budget here was huge. You had 4 fluorines, each was 7, that's 28. And then xenon is in group 18, minus 10 is 8. So this is actually 36, and that's a lot. So let me do this real quick. And can y'all see, are y'all seeing a molecule, like a purple dot in the middle? You can chat, you can unmute, you can tell me whatever. Or on your screen, are you seeing a purple dot? Yes. Okay, thank you. Thank you. Okay, I just want to make sure I'm not screwing stuff up. So this is I want y'all to think about the shape. Not that we're going to do a lot of it today. Just kind of end with it. So let's think about that xenon thing that you just did. You had 4 fluorines attached to it, right? So 1, 2, 3, 4. So that's what 4 fluorines would look like, right? But we also had a lone pair. And when we add lone pairs, it changes the shape. Now, so the question before we go is, why are all those things trying to get away from each other? Why, when you try and get this fluorine close to the other ones, why do they run away? Does anybody know the answer to that? You can unmute or you can say it. Abigail, excellent. Connor, great. Yes, those electrons repel each other, just like we talked about at the beginning. Electrons really hate each other, and so they're going to get as far away from each other. So listen to the letters. Valence, V, shell. So valence shell, outermost electrons, that's what we're dealing with. Electron pair, repulsion theory, VSEPR, or Vesper theory, tells us when you draw a Lewis structure, how you find the shape. So that was great answers from everybody. Okay, so just so everybody can keep track, next week we're going to meet at 1 o'clock on Thursday, just because Matt initially told us November, and I think that was wishful thinking on his part. But come back, and we're going to take these very same molecules that we drew. Maybe I'll give you another one because they were hard, and maybe I can find a harder one. And we'll give y'all take these very same molecules, and we'll do a little bit more with them. But for now, that's all I had. Thank you guys so much for coming today. And if you have questions, I'm willing to stay on and talk to you. Or if you have questions, you can put them in the chat box. But thank you so much.